Hello and welcome. In this video, we'll go over closed reacting processes involving chemical equilibrium. It's covered in chapter 14. In chapter 13, combustion is covered, and most combustion reactions, the reaction is given to us. Whereas in this case, we do not know the product's composition, and a chemical equilibrium analysis produces product's composition for us. And how is it done? Essentially, the theory shows that at a given pressure and temperature, if you leave some chemicals inside at constant pressure and temperature, the second law and first law will dictate the reversible work produced by that you can extract will maximize, or the Gibbs function will minimize, and at that time will reach chemical equilibrium. To put it more mathematically, it's shown here, this reacting chamber. Suppose a mixture of ideal gases is coming in, and they're subjected to a pressure and temperature, PE and TE. Then it can be shown that the difference in Gibbs function of the mixture is really what drives the equilibrium. In other words, minimizing the Gibbs function or maximizing the reversible work takes you to that product's composition. So one of the ways to solve the problem computationally is to guess the product's composition, and the one that minimizes the Gibbs function is the desired composition. And there are other ways to solve chemical equilibrium problem. In this case, we are showing a CO2 going into a chamber subjected to a very high temperature, and it breaks up into CO, O, etc. It's an incomplete reaction, as you can see. And that's called overall reaction. That's our goal, to find out what will happen to CO2, how much CO is produced, etc. at a given pressure and temperature. But you can break it up. To solve this problem, you can break it up into elementary steps and analyze those to create the composition. We'll bypass this process using test. So let's go ahead and try to analyze this particular problem, dissociation of CO2. First, let's go to the state panel. We'll take a flow state, and this is the NIGE model, ideal gas equilibrium model, that handles chemical reaction, chemical equilibrium between in a mixture. So, for instance, in this case, the composition panel should be familiar if you have gone through the combustion video. So let's say we have CO2. We add that. That's our reactants. And the products, we don't know their amount. That's why there is no, notice that here we could assign the value, how many kg or how many kilomole. We have added 1 kg of CO2. And we don't know what the products are. We could add all of them, or just to be compatible with the animation I just showed, let's just pick oxygen, CO2, CO, and O. We add those, and we don't know the amounts. So let's say we subject the reactants. The reactants is coming at 100 kPa, 300 Kelvin. We could assign a mass flow rate, but otherwise we'll pick up the mass flow is 1 kg per second that we set up. So let's say we have 1 kg of CO2 coming at 100 kPa, 300 Kelvin, and we are heating it up at constant pressure without changing the pressure to, let's say, very high temperature, let's say 2500 Kelvin. If we do a calculate here, what should happen is that now that we know the pressure and temperature, it will minimize the Gibbs function and evaluate the composition. If you go back to the composition panel, you will see that the product's composition is shown in this pie chart, and these are the different mass fraction and mole fraction of different components. Obviously, the incomplete reaction, which is balanced, is shown here. And this must be 1 kg of CO2 producing so many kg of O2, so many kilomoles of O2, CO2, etc. But the left hand side is 1 kilogram, the right hand side must be 1 kilogram. Okay, so let's go and evaluate. Now that we know the state, suppose the question is determine the heat transfer. We can, even though there is no process panel here, we could just evaluate that quickly. Q dot must be equals m dot 1 times H2 minus H1. Notice there is no change in interpretation of states in the IO panel. IO panel is oblivious whether there is a chemical equilibrium or anything else going on in the state panel. It picks up H2 and H1 and gives us the heat transfer. So you must be hitting it. This is in SI units. About 3.6 million joules of heat might be supplied to reach this final state. Let's have a combustion problem, a more challenging one. So we go to closed system, closed processes, and combustion and chemical equilibrium, and NIGE model will take us to closed processes. Combustion reactions are set up slightly differently than general mixtures. So let's say we have a tank of 10 meter cube filled with methane and pure oxygen. Let's say we have methane, where is methane? Here, 1 kilomole of methane, and oxidizer, we pick, let's say we pick a particular reaction. Let's say we want to balance with pure oxygen. So we can equilibrium combustion with known oxygen, pure oxygen, 100%, execute. So it will pick up oxygen. So this is my reaction right now. If you go down, methane and pure oxygen producing products, but we have to go and assign what products we want. You can add them all, or you can click the select typical products button that selects typical products that is found in a chemical equilibrium situation. Okay, so as you can see, the composition is not known. We just picked a bunch of products. In NASA equilibrium code, for instance, you can choose thousands of products, but for energetic purposes, you don't need thousands of products. Those are really minute. Many products are really minute. Okay, so now that we have set up the reactants, let's go and find out the state. Let's say we have at 100 kPa, 10 meter cube, at 300 Kelvin, and we cannot specify the volume also. So let's say we have a tank of 74 meter cube containing 80 kg of methane air mixture, and we have a temperature 300 Kelvin. Obviously, we could change the methane, the reactants amount by multiplying the reaction, and we can have, instead of specifying temperature, we could specify volume, or pressure, we could just specify volume. So anyway, finding the reactant state is a fairly easy process. It's ideal gas, purely ideal gas equation, but it does show you all the partial properties of each component. Now this is state 2. We are going to minimize Gibbs function to find the composition, and pressure and temperature must be supplied. So suppose we have a constant pressure process, so P equals P1, and let's say the temperature, let's supply a very high temperature. Temperature must be known. With that, if I calculate, then we can get the composition for 3000 Kelvin, and you can come back to the reaction panel and see the pie chart, and the reaction is completely balanced. Now suppose we are after finding the adiabatic flame temperature. In other words, what temperature would be if there is no heat transfer. Obviously, if you go to the process panel, you load state 1 and state 2, and when you calculate, you'll find in this case there is boundary work and there is heat transfer involved. In fact, negative number means heat must have been lost. So we have cooled the products to get the final temperature. To find adiabatic temperature, we have to go do trial and error. We have to go back here and say, you know what, maybe the temperature is not 3000, maybe it's 3500. Of course, the composition is recalculated. You come back here and it's updated. Look, this is not positive, Q is positive. So the temperature, adiabatic temperature will be somewhere between 3000 and 5000 Kelvin. Notice that the boundary work is automatically calculated because the process is a constant pressure process. If it's a constant volume process, the WB will be automatically calculated to be 0. So in other words, for an equilibrium reaction, you have to know the pressure and temperature for the calculation to proceed. And in many problems where you do not know, one of the desired answers says the temperature or the pressure, you have to keep guessing until the energy equation is satisfied in the process panel. Whatever the condition is given to you is satisfied here.